Hey guys, welcome back. It's Mrs. Webb here again. So we're going to spend a little bit of time today talking about average velocity. So in our last lesson we chatted about average speed specifically, and I introduced the term scalar to you guys last time. And if you remember from our last lesson, a scalar quantity is a quantity that has a magnitude but it doesn't have a direction. So when we talk about scalar quantities, that was like our distance, right? Our distance traveled between points A and B. There's a magnitude to that separation between A and B. In my example here, it's 1.2 kilometers. And we talked about our time, and our time was also a scalar quantity. In this case, in this example, 50 seconds. Some other examples of scalar quantities would be things like temperature, 100 degrees Celsius, or average speed, 30 kilometers per hour, right? All those values have a magnitude associated with them, but you can see that there's no direction, right? A vector quantity is what we're going to chat about today, and we're going to practice together in class time. A vector quantity is a quantity that has magnitude, but it's also been given a direction. So there's a direction that's associated to that magnitude. So for example, if instead of talking about 1.2 kilometers, now I add a direction to it. So I say, the students ran 1.2 kilometers, but now I say they ran west. That right there is your definition of a vector. It's a magnitude with a direction attached to it. And the way we represent vectors is using an arrow. An arrow represents the vector. And the other thing to keep in mind is that the length of that vector, of that arrow, the length of that arrow also represents the magnitude of that particular vector quantity. So if I had one length that was 1.2 kilometers versus another length that was, let's say, double that speed, if I was going to draw that out for you guys, maybe for this particular magnitude and direction, I have somebody is moving, right, let's say 3 squares, right? And then I want to represent a second person that's traveling to the right, but they're traveling double that spacing. So they travel 6 squares. My vector arrows need to be drawn to an appropriate length in order to represent that this particular magnitude is twice as much as this particular magnitude. So we're going to get into vector diagrams shortly, but that's something to keep in mind as well. The other thing too is that here I'm using delta D, but I've placed an arrow on top of it. That arrow that I've placed on top of the variable is representative of a vector quantity. So whenever you see a little arrow on top of your variable, you know that you're dealing with something that has a magnitude and a direction. In this case, we don't call this distance anymore. We actually call this displacement. We'll define that for you momentarily. Another vector example would be something like gravity, right? Gravity has an acceleration of 9.81 meters per second squared downward, right? So gravity is always pulling you down toward the center of the earth. Average velocity, right, versus average speed. Remember, as soon as you see this arrow on top, this is giving us something slightly different. So average velocity is 4.3 meters per second forward, right? So whatever object is moving in the forward direction. So those are some examples of vectors. Biggest things to remember is that your vector will always have your direction shown in square brackets, And the variable will always carry a little arrow over top of it to indicate that it's a vector and not a scalar quantity. Now, displacement. Now, I want to talk about displacement because this is something we're going to work with today. Displacement is different than distance. Yes, they're both represented by a lowercase d. But when we talk about displacement, what we're talking about is the change in position, in the position of the object from a starting reference point. So, for example, if you go from your house, that's your starting reference point. You travel to school, you go to class, you go to lunch, you go to class again, and then you come back home. Your total distance may be something like, let's say 12 kilometers or so, right? You've got a ton of steps accumulated, you've actually put on quite a bit of mileage throughout the day. That's my total distance, right? That's the spacing that I've accumulated from home to school to class to lunch to class again and then back home. If I'm talking about displacement and I'm looking at, with respect to my home, how much have I removed myself? Well, in that case, my displacement is 0 because I started at my house. Yes, I went all over the place and I may have been gone all day long, but at the end of the day, I came back to my house. So I have not removed myself at all from that starting reference point. So my total displacement in this case is 0 meters, which is kind of, if you're one of those people that counts your steps and all that, it's kind of defeating because, you put it on all these steps, and then all of a sudden when you look at it in terms of displacement, you really didn't do anything. So anyways, but that's the big difference, and it's an important difference to keep in mind because it changes how we look at things. Everything in this kinematics is very dependent on how we're observing it, right? Everything is relative. You might have heard that saying before. So when we talk about average velocity, the reason I've introduced this displacement term to you is because when we talk about average velocity is the total displacement of the object over a period of time. If you remember when we talked about average speed, we talked about the total distance that the object travels over a period of time. Well, now we don't really care how much, distance was covered throughout the day. What we care about is what was the displacement from that reference point, right? So in this case, we want to also remember that when we talk about this delta displacement, we're referring to our first displacement plus our second displacement plus our third displacement, and so on and so on. And our time, again, is time 1 plus time 2 plus time 3 plus, and on and on and on. Okay, so the formula is very similar to our average velocity, but we're not taking into account the entire distance. So if I go back to this example up here, if my displacement was 0 meters over the entire day, it doesn't matter if I was gone, 14 hours. My average velocity for that particular day would have been 0 meters per hour because I started and I finished at the exact same point. Versus if I calculated my average speed, in that case, I would have a different value. So I want to give you a couple of other things that we have to take into account before we start talking about calculations. The first thing is our displacement. Second thing is remembering that this delta displacement refers to our displacement 1 plus our displacement 2 plus our displacement 3. And then our delta time refers to time 1 plus time 2 plus time 3, and on and on and on, right? It's the sum of those displacements and the sum of those times. The thing to keep in mind when we're doing calculations that involve vectors is that we need to assign a positive sign and a negative sign to our magnitudes. That's how, when we're calculating, that's how we assign a direction to our magnitudes in the calculations. And the way we assign our signs is we use a rosetta. So on our long answer problem, now what we have to do is we have to insert a rosetta to indicate what we are going to call positive and what we are going to call negative on our particular calculation. If it's a 1D problem, where we're just walking back and forth, or we're moving up and down, so maybe walking along a sidewalk, moving in an elevator. If we're just traveling in one plane, typically when we assign a direction, the right is going to be your positive and the left is going to be your negative. And typically, if it's an up and down problem, your up is going to be your positive and your down is going to be your negative. That's the typical way that the positives and negatives are assigned. And in some instances, and we will chat about this, when we get to projectiles and gravity and all that kind of stuff. But in some instances, it's more beneficial for us to assign the reverse. The left is the positive or the down is the positive. But we'll cover that when we get there. For now, usually we'll assign the right as positive and the up as positive. If we have a two-dimensional scenario, which we'll talk about as well when we start talking about traveling northwest or whatever, what have you. Typically when we're talking about a two-dimensional range of motion, we talk about the up and the right being positive, or the north and the east being positive, and the down and the left being negative, or the south and the west being negative. So that's kind of the conventional things. Truthfully, when you're doing any sort of problems, you can assign, whatever you want to be positive and whatever you want to be negative. It's just that sometimes your calculations get harder if you don't follow the convention, because you end up dealing with lots of negative signs, and that ends up causing some issues. So we're going to do a lot of examples together so that you see, but keep in mind, again, if you're keeping a study sheet, typically we say right and up is positive, down and left is negative. The other thing that we have to do when we do vector calculations is we have to draw a vector diagram. So on your long answer problem, now if it's a vector problem, you have to include your rosetta and you have to include your vector diagram, right? And then everything else is the same. You would include your formula, you would sub your values in with their units, and then you would solve for your problem. The thing with a vector diagram is that it's really important that you're able to visualize what it is the problem is telling you, so that you draw your vector diagram correctly. And if you draw your vector diagram correctly, you will solve your vector problem correctly. Typically, if you draw your diagram incorrectly, it'll lead to an incorrect solution. So it's very important that you're able to draw these diagrams properly. And typically I tell my students, I know that the impetus is to just start as fast as possible, start calculating, start setting things up, using formulas, putting it in your calculator. But if you can just take 30 seconds, take a minute to just visualize what is happening. That's a nice thing about physics, is that a lot of the stuff we're talking about here at the beginning, you can actually visualize these scenarios. And so take a moment, visualize what's happening, see the problem in your mind's eye, so that when you start calculating, you can, look at your final result and think to yourself, does this make sense? Okay. Now, the tip-to-tail method that I was mentioning above, the tip-to-tail method is a method that we use to draw vector diagrams. And the gist of it is that the tail of the subsequent arrow always touches the tip of the previous arrow. So I have the tail of vector 2 touches the tip of vector 1. The tail of vector 3 touches the tip of vector 2. So if I was to draw a vector diagram, here's my starting point. This particular person or object or whatever displaces itself in this direction, right? So they start here, let's say it's a student going for a hike. They hike in this direction for, X amount of meters or kilometers. They stop, they have lunch, they look at the scenery, and then they continue on their walk, but they change course. So from this stopping point, they turn themselves in kind of this northwesterly direction, and they hike for a longer distance, longer displacement. Then they stop, they take a picture, maybe they, have a snack, and then they turn around and they travel in the southeasterly direction for a fair amount of time, for quite a displacement here. And this is where they finish their hike. Okay. This separation here is their displacement. This is how far they've displaced themselves from their original starting point. If I add these distances together, that's their total distance traveled. This is their displacement traveled. Okay. Now, the tip to tail method, if you notice in this first segment here, the tail of the second vector is touching the tip of the first. They travel a third displacement here. The tail of that third vector is touching the tip of the second vector. And then displacement, or the resulting vector, always starts tail to tail with the first vector, and it finishes tip to tip with the last vector. Okay, so I'm going to give you an example down here. We have Nick. Nick asked to go to the bathroom, and he leaves the class and travels 2 meters left to his locker. He then travels 4 meters right to the water fountain, and finally he travels 1 meter right to the bathroom. We need to find a couple of things. So we need to find what's the distance traveled. We need to find Nick's displacement. We need to find Nick's average speed if he took 5 minutes to make the trip, and we need to find Nick's average velocity. Okay, that's all of the things we want to do. So this is a long answer problem. A couple of things we need to do first right off the bat. First thing is we're going to draw, because eventually we are going to be talking about displacements and velocities. So first thing we need to do is we need to draw our vector diagram and our rosetta. So I'm going to put my rosetta here. We're traveling in a 1D plane. I'm going to follow my convention and say right is positive and left is negative. Okay. And you don't have to draw in a test, obviously. You don't have to draw anything near as detailed as what I'm going to do right now, but why not have a little fun with it right now while we're learning about vector diagrams. So I'm just going to put our hallway here. Whoa, what just happened? All this for me to get a straight line. Hey, guys? Okay. Let's try that again. Okay, so there's my hallway. Here's my classroom. Here's Nick heading out the door with his cool red hat. Nick, when he leaves, and we're going to maybe use, let's say, a thicker pen here. I'm going to use this light blue color. Nick, when he leaves the room, he travels 2 meters to the left. And I'm going to say, let's just say 2 meters because I'm using my square paper. Let's say 2 meters is 4 boxes. Okay, so he travels 2 meters to the left. 2 meters. And I don't need to put my square brackets here because my arrow is indicating the direction of travel. So he travels 2 meters to the left and he goes to his locker. So I'm just going to put his locker right here. Okay, there's his locker. Hangs out there for a little while. And then he travels another 4 meters to the right. So remember, my arrow has to be indicative of the magnitude. So I'm going to make my 4 meters. There's the tail of my next displacement. And it's attached more or less to the tip of my first. Now I'm just separating these slightly so that we can actually view the two arrows without them being one on top of the other. It just makes it easier for us to see. And I've made this arrow twice as long as this arrow because in this particular segment, Nick travels 4 meters. And he travels to the right. Now, he stops at the water fountain. So let's put our little water fountain in here. And then from there, he goes over to the washroom finally. And he only travels 1 meter. So the washroom is very, very close to the water fountain. Okay, so there's my 1 meter. And notice that my 1 meter vector is representative of that 1 meter magnitude. Right, so my 1 meter magnitude is taking up 2 blocks here. My 2 meter magnitude is taking up 4 blocks. My 4 meter magnitude is taking up 8 blocks. So all of these vector arrows are representative of the magnitudes that they're showing. The other thing is, note that the way I've done this vector diagram, I started here at the classroom door. Nick travels to the left. From there, that's where I place my second arrow, my second vector, traveling to the right, stops at the water fountain, and then my third arrow attaches tail to tip and shows where Nick moves from there. And from there, he travels over to the bathroom. Okay. And that's where he stops. So we got to figure out a couple of things. I'm just going to shorten this diagram a little bit here. We have to figure out first, part A, we want to figure out what is the distance that Nick traveled. Now remember, distance is a scalar quantity. It's not a vector quantity. So for my distance, I want to figure out delta D. There's no arrow on top of it because it's scalar. Delta D corresponds to D1 plus D2 plus D3 because there's 3 distances that he travels. And in the first distance, he travels 2 meters. In the second distance, he travels 4 meters. In the third distance, he travels 1 meter, which means that our distance, our total distance traveled is 7 meters. Okay, that's how far Nick travels on his way to the bathroom. Okay, so that's the first thing. The second question, part B, is asking, well, we know his distance, but what is his displacement? So now we want to look at this in respect to his displacement from that starting point. And so here, our total displacement is displacement 1 plus displacement 2 plus displacement 3. And when we look at vectors, we have to assign a positive or a negative in order to show the direction of that particular displacement or that particular vector. Notice that my Rosetta, where's my arrow? My Rosetta that I placed above my picture tells me what is a positive and what is a negative. So in this first segment, the 2 meters, he traveled left. And in my Rosetta, I'm saying that left is negative. So that means that he travels negative 2 meters. Plus, for my second segment, my arrow is pointing to the right, which is positive. So 4 meters. And then my third segment is positive 1, so 1 meter. That means that my total displacement is going to be 3 meters. So negative 2 plus 4 gives us plus 2. Plus 1 gives us 3 meters. So you can see that his displacement is different than his total distance. Okay, so that's the first part. This is your scalar quantity. This is your vector quantity. And I forgot to put one thing here. The fact that this is a positive, and let me take out this because I'm not quite done here. The fact that this is a positive number is important, right? So the fact that we ended up with a positive 3 meters is important to our final answer. Because what that positive 3 meters means is that we traveled 3 meters, and positive based on my Rosetta is right. So Nick displaces himself 3 meters to the right. Okay. That sign that's attached to the magnitude, that sign is going to become your direction. Okay. The third question is, and I'll do this one over here. The third question was, well, what is Nick's average speed if he took 5 minutes to make the trip? Remember that average speed is our total distance over our total time, and that's the same as our distance 1 plus our distance 2 plus our distance 3 over our total time. So that means our V average is 7 meters, and Nick took a total of 5 minutes to make that trip. So he wasn't rushing by any means to travel 7 meters. And this is 1.4 meters per minute. If I'm looking at significant digits, I probably would do this as 1 meter per minute. I'm going to keep that decimal there for now, just because. Okay, so that's his average. So definitely, not moving very quickly at all. The last part is, well, what is his average velocity? And average velocity is the displacement, the total displacement over the total time. So that's my first displacement plus my second displacement plus my third displacement over my total time. And we determined that our average displacement is positive 3 meters. And it took him 5 minutes to, cover those positive 3 meters. Okay. And so that tells us that if Nick was traveling 3 meters in 5 minutes, he was traveling at a whopping speed, at a whopping velocity of positive 0.6 meters per minute. He was flying, so to speak, right? Now, remember, this positive sign is important because this positive sign tells me the direction that velocity vector would point. And so this is 0.6 meters per minute to the right. So we're going to give this a lot of practice during class time. Really important to get used to talking about the positive and negative directions, and remembering that positive and negative they indicate what the direction is of that particular vector. So you've got to keep them straight as you're doing your calculations. We will chat about this in class time. If you've got questions, let me know. And as always, guys, I hope you're doing well. Take care for now.